afternoon, everybody. Without further ado, we'll start. My name is Abdul Farrab. This is Mohammed Arabi. Our topic is testing of axially loaded upvc pipes filled with concrete. Okay, this is our outline. Okay, first of all, concrete filled. We're using concrete filled upvc tubes as a compression member. Basically, we're getting UPVC pipes, cutting them up to different lengths, and cast concrete inside them. Then we wait for 28 days until it gains its strength, and then we perform the testing. Okay? We're going to compare this, after we get our results, we're going to be comparing this to reinforced concrete columns. And one of the reasons we're doing this is that there are several advantages of plastic over steel. These include that plastic is non-corrosive, it's a lot lighter in weight, and it's more practical, it's easier, and it leaves a smooth surface at the end. Okay. There's no need for scaffolding, no need for shuttering, no need for plastering. And this reduces material and labor costs involved in the processes that it reduces. Okay, there was one article I found relevant to this topic. The name of the article is Concrete Filled Structural Plastic Columns by Carl Kurt. It was published in ASCE Structural Division Journal in 1978. Mainly their problem was that they were trying to see how plastic increases the strength of the short concrete core, and the influence of the slenderness ratio on the ultimate strength. Okay. And the methodology was that they casted several different specimens with two plastic material, ABS and PVC, with different slenderness ratios and different tube wall thicknesses. Okay. And for the reliability of the results, they casted 3 specimens for each slenderness ratio. Okay. And then the conclusion that they came with is that the plastic provided sufficient lateral support, which increased the ultimate strength of the concrete core. Okay. And the increase in the concrete strength core was approximately found to be 3.25 times the burst pressure of the tube. Okay? And they recommended testing other concrete design strengths, which is what we're doing. Okay? Our objective is to investigate the behavior of concrete filled UPVC tube columns subject to axial compression. By behavior, we mean stiffness, the axial shortening of the concrete at failure, the ultimate load the confined specimen can take, the effect of buckling by testing a long specimen, and the potential mode of failure. And our scope includes short and long columns, various pipe wall thicknesses, and different concrete compressive strengths. I'll explain the theoretical background for our experiment. Normally, in an unconfined concrete column, axial shortening takes place, and due to Poisson's effect, transverse expansion takes place because the volume of the specimen must remain constant. Okay? When the specimen is confined, the transverse expansion is less, and therefore, to maintain the constant volume, the axial shortening is less too. And this makes the concrete core stronger. Okay, here in this diagram is P note is the reaction when the concrete core expands. It applies pressure on the confining tube, and then the reaction of this pressure is P note, or negative P note in this case, because in our case the P note is the pressure applied by the edge of the concrete core on the plastic tube. And we denote A as the radius of the concrete core. Okay, these are the stresses in the concrete. First of all, due to the applied load, the axial load, it's subject to normal axial load, which is denoted here as sigma z, and sigma z is equal to just to the applied load divided by the area, which is pi d squared over 4. Okay. And then due to the confining effect of the pipe that's surrounding the concrete core, the concrete is also subject to it's triaxially compressed. In the latter direction, it's subjected to sigma r, which is a radial compression, and sigma theta, which is tangential hoop or hoop compression. At r for the concrete core, at r equals a, at the edge, the radial stress is equivalent to the tangential stress, also equivalent to the P naught, which is the pressure applied by the tube on the concrete, which is in contact with. Okay, the stresses in the UPVC. First of all, we assume that the concrete core takes all the axial compression. So you don't see here in the diagram, you don't see an axial component. But in the transverse directions, the PVC is subject to a tangential stress, which is tension, and radial stress in compression. Okay. And in the diagrams, they show the distribution of both the radial and tangential stresses through the pipe thickness. For the tangential stress, it's a maximum at the inner diameter of at the inner radius, and then it reduces to a minimum at the maximum radius, which is b. As for the radial stress, it's zero at the edge of the tube, because nothing is in contact with the edge of the tube, and it increases at the inner radius. Okay, the radial strain for concrete is as follows, and it's sigma r is equivalent to 1 divided by the modulus of elasticity of concrete times the radial stress minus the concrete Poisson's ratio times the axial stress and the angular stress, or the tangential stress, and the radial strain for the UPVC is equal to 1 divided by the modulus of elasticity of the plastic multiplied by the radial stress minus the Poisson's ratio of plastic multiplied by the angular stress of the PVC. At r equals a, the radial expansion of the concrete is equal to the radial expansion of the pipe, because both at r equals a, both the pipe and the concrete are in contact. If we integrate both of these strains by their respective volumes and equate them to each other due to the boundary condition of the fact that since the edge of the concrete is touching the pipe, that both the expansion of the concrete and the pipe have to be equal, then we get this. We end up with this expression for this is the confining pressure for pipes. And this expression could be limited down. This expression is a general expression for thick and thin pipes, thin-walled pipes. But for thin-walled pipes, it could be limited down to P naught is equal to 2 times the angular stress times the wall thickness divided by the diameter. Okay? From this, we can note that the confining pressure exerted by the pipe on the concrete, which is what from our theory we need to give the concrete core its strength, the confining pressure is proportional to the concrete's Poisson's ratio and the ratio of the modulus of elasticity of the plastic divided by the modulus of elasticity of the concrete. And it's also inversely proportional to the ratio of the radius to the thickness to the wall thickness and the Poisson's ratio of the plastic.
Okay. And here is the description of our samples and preparing it. I put a code for every sample. This is CP means complete filled pipes, because we have both pipes with concrete and plain concrete without pipes. So CP mean with pipes. This 300 is the height of the sample, and 25 is the strength of concrete, because we have two different strengths, and 4 is the bar of the pipe, because we have 4 different bars. Okay, and here's and a picture for every sample. This one is the pipe, this one is the pipe, and this one, because of the ground column, we use minimum reinforcement to decrease shrinkage, and because it was very hard to apply the test of compression test on a long column with diameter 15 centimeter, long column about 240 centimeter and 300 centimeter without any reinforcement. It was very hard to just apply the test on a plain concrete. Here is a table that shows all the samples we have. As I said, we have complete filled upvc pipes, and another one, it's plain concrete cylinders. We have FCU, different FCU, complete strength, 25 megapascal and 35 megapascal. These are the short column samples. Here's 50 centimeter, 60 centimeter, and 180 centimeter. And these are the different bars. This 4 bar, 6 bar, 10 bar, and 16 bar. All of these casting pipes have done, but we didn't yet do the samples of the long columns. We didn't yet cast it with concrete. Here's also the long columns, different concrete strength, different bars with height 140 centimeter and 300 centimeter, sorry. And for the plain concrete, we use minimum reinforcement, just as I said before, to hold for testing and to decrease shrinkage and to avoid tension in concrete. Here is the next design we use for the 25 megapascal and 35, and the amount of every component: cement, water, oil aggregate, coarse aggregate, and soil plasticizer. We only use it in the 35 megapascals. Here are pictures for cutting the pipes with the heights we needed, because the standards of the pipe from the company we got is 6 meters. So we had to cut it as you can see here for the heights we need. It's 180, and this is the cutting saw we're using. And here we're aiming to do it as flat as we can, so that the surface will be flat while testing. Here are some tools we used while casting the pipes. This is a steel end for the pipe to avoid the concrete from going out of the pipe. We use it at first, and then we had some problems with it, because when we put the sample out, it was broken because it was very tight on the pipe. So while removing it, the concrete, there were cracks in the concrete. So we think of using a plaster like this to avoid it from moving. Also, but what we got also not as good results as we were aiming, as you can see here. So at finally we use like a circle of plastic sheet. We put it to avoid this marks in the concrete. But also we didn't get the perfect result we were aiming. That's why we are going to do capping for all the specimens, and I'll show later in the slide. For the short columns, 60, as you can see, and in between is about 30 centimeter. We don't have a problem. We just put it on the floor and cast it. We don't have any problem with it. But for the 240 and 300 centimeter, it's very high and it's very difficult as well to cast it. Just like it on the, if it's standing on the floor alone. So we made a frame, a wooden frame with 16 openings, just as the diameter of the pipe. And as you can see here, we put the pipes inside. That's our mixing of concrete. So, as I said, we have two different concrete strengths. I said before, for the short columns, we don't have any problems with filling it with concrete, but for the long columns, we use this cone, and we take it up with the crane, as you can see here. And this is the compactor. As after each sample is filled with concrete, we use a compactor to avoid the voids. Okay. As I said before, we had some problems after filling the tarps with concrete. That's one problem, shrinkage, and that's why we are going to look at it. The surface of concrete decreases than the surface of the pipe itself. And here, this is a result of using the steel entering cap at first, because when we got out the pipe, some of the concrete stayed in this steel, and it didn't come out. So we had, it's not a very flat surface, and it's not a good result. That's why we are going to do capping. Our methodology of doing capping, the first, we have this steel, and now we use it first to hold the pipes inside. We will cut it. We will take a cylinder of 10 centimeter, and this 10 centimeter, we'll put it here on each pipe with one height more than the pipe, 1 centimeter, and we'll use stick and rod to ensure that the surface will be exactly flat. And that's why we are aiming to be flat, because the test, our compression test, the test should be flat, the specimen should be straight, the axial loading should be exactly in the center, as I will show you here, as Hakim will show you.
Basically, 4 precautions we have to, before doing our test, to ensure that the results we obtain will be reliable. Because we don't want to do the tests and come up with the conclusion that the results we came up with are inconclusive. So basically, first of all, we have to ensure that the surface of the specimen is even, and that the surface is perpendicular to the axis. The samples are straight without imperfection, because the samples could be slanted due to the pipe material itself. And last but not least, the loading must be concentric, because all of these factors are related to the fact that if the loading being concentric, if these factors aren't ensured, the specimen could be subject to movement. Okay, and this is the testing setup. This is the test machine. These are steel columns. This is steel frame. This is the load cell. This is the specimen in the middle, and this is an LVDT to measure the formation. Okay, the expected outcome from this thesis is to acquire a better understanding of the compression behavior of short and long filled UPVC columns. Okay. Another outcome is to conduct experimental work more towards a full scale than small specimens, and to explore the potential usefulness of UPVC tubes in strengthening columns.
Okay, cutting and handling our pipes. At first, we use a machine in the workshop, the mechanical workshop, but suddenly we had a problem that the machine stops working. So as I showed before, we used the cutting saw from the architecture lab. It's not so easy to get the pipe so flat at the beginning, at least. It wasn't so easy, but by cutting more pipes and by this, by practicing, at the end we had a better results for cutting the pipes. Material procurement in large quantities. For getting the pipes, we had lots of problems, because you can find some bars in some companies and another bars in other factories. So we wanted to get the same material from the same company or factory because we already have different variables, so we wanted the quality and the material itself to be the same. Also, we had some for different bars, they aren't available in the market, for the 16 bar, for example. And one pipe, it was, it had about imperfection in the pipe itself, it wasn't straight. We are aiming to avoid these problems while testing, while obtaining and operating equipment. We get the frame for the round columns. We got also the steel end for the pipes for the beginning. Also for getting out the pipes itself from the frame after being casted with concrete. It was very heavy, so we get a handle. I forgot to put the picture, I'm sorry. We got a handle exactly the same diameter, or half centimeter less than the diameter of the pipe, with two hands at both sides, and we'll take it off by the crane as well. For the unconfined samples, I think I'll say this.
For the unconfined samples, we're doing plain concrete samples. So we, as molds, we propose to do to use the plastic, the PVC as molds, but to cut them vertically. But then the problem with this, when we were casting the 30 centimeter specimen, was that we found that the concrete had cracks, because this is the molds were used as specimen and they were cut vertically. So the concrete is stuck to is supposed to be stuck when it expands to the plastic. Since the plastic is cut, it didn't provide good enough support for the specimen, so there were cracks in the specimen. So then what we're going to do instead is we're going to leave these, we're going to cast them in PVC, and we won't cut them until the day we come to test, and we're going to cut them with and when we cut them, it leaves a slight mark on the concrete, but that's not a big problem. Instead of just cutting up vertical molds and taking them off instantly. Okay, and this is our revised schedule. On Monday, the 19th, and on the 20th, we're going to cast our long columns, the 240 centimeter and the 300 centimeter columns. Okay, and as for the testing, their time to be 28 days after specific groups of specimen have been casted. Okay. So one is on the 22nd of November, the other is on the 29th, and so on. And we estimate that we're going to, for each set of results that come up, we're going to need approximately 5 days to come up with something conclusive. Okay. These are our references, and thank you.
When the concrete sets, it shrinks.
Yes.
That means the concrete inside the pipe will shrink. So there is you don't have full contact between the concrete surface inside the pipe and the plastic pipe. That kind of an interaction, you assume that they are completely in contact in your theoretical analysis. That's why you said P node in the concrete is equal to the P node in the tube. What are you going to do about this? But that means you're going to have to push the concrete very much, large deflection, so it would go lateral before it touches the inside of the pipe.
But then when the concrete gets loaded, it's going to expand, so there will be contact, and maybe at zero load there won't be any contact.
Yes, that's what I'm saying. You're going to have to push the concrete first,
Yes.
initially at no contact. The concrete will behave on its own, and hopefully it will give you lateral deformation using Poisson's ratio and so on. You need to calculate that. You see, you need to know how much load you have on the concrete, enough to get it to expand laterally or to bulge laterally to start the concrete pipe interaction. Another method of doing that is using non-shrinkage cement or paint. You already poured the concrete, right? Okay. So didn't you notice that there's a gap between the concrete and the pipe?
We noticed at the top.
The top, of course, is shrunk. I mean, the concrete shrinks in every direction. So you notice the top, but did you notice something?
We didn't notice the
The
difference
sides.
between just the concrete itself and the pipe.
It's going to be very, very small shrinkage. But you need to analyze that and find out how much load the concrete will have to take before it stops acting with the PVC. Thank you.
Once again, there's a point, good point. But the hypothesis of concrete shrinkage. Concrete shrinkage because it moves water, right?
Yes.
What about your pipes? How much water will concrete lose during cement dehydration? Will you have that amount? My question is, will you have that amount of shrinkage? Dr. Safwan is saying, you mentioned that you didn't include it,
Yes.
but that doesn't mean that you don't have to think about it, right? So, do you think it will shrink that much?
Those are being covered on sides, not as much as on the top, on both ends. I think so.
What is
So,
the
please
shrinkage
understand my point.
from the top?
Misunderstand. Yes, the concrete will shrink.
Yes.
The main reason for concrete shrinkage is
Evaporation.
and losing water and dehydration of cement, right? With all this confinement, and you have your concrete inside that PVC tube, will it shrink much? Will it leave some gaps? And if it does, will your axial force compensate for those gaps?
I think we can get this shrinkage after cutting the pipes and cutting out the specimen itself or the concrete. We can get
What actually I want to hear is, I will calculate the amount of shrinkage and see how much. I don't know how, right? Because you have a weird situation. It's not common concrete. You have to look at it.
It's not on the concrete.
Like, it's not like a slab which is exposed to 40% humidity which is in the code. And we can calculate the shrinkage based on this environmental completion, right? It's different. So how we are going to calculate that amount?
I have a comment on this. The shrinkage of the concrete in the across the diameter is almost negligible because the diameter is 15 centimeters compared to the length. The length is so long, so the main shrinkage will take place in the axial direction,
Not on the lateral.
not in the left. If we multiply the shrinkage strain by 15 centimeters, it will be very small quantity, and that's why it was not noticed actually in any of the specimens that we have circumferential cracks between the pipe and the concrete. Maybe some of your specimens you had less amount of concrete poured at the top. It's not shrinkage. It is because when you compacted the concrete, because of the vibrator, part of the concrete went out, and then you didn't refill. But some of the specimen, I believe that it was not.
we filled all the pipes.
Some of them-
Dr. Hua, I agree with what you're saying, but the fact that it's small on the cross section in terms of magnitude, it will be translated into a small
Very small.
stress strain. So in other words, it's small in absolute magnitude, but I also agree with you and with our colleagues that because it's unusual specimen in terms of being tall
Right.
and not wide, the amount of shrinkage, I don't think it will cause a reason or be a reason for having a full separation. What you talked about is, I would assume it's right because that's settlement concrete, And yes, as Sushman mentioned, underloading, there will be some kind of strain, lateral strain, enough to get that contact in place. So it's something that's worth looking into, but I don't think it will jeopardize the experimental. And of course, it provides the cement as it hydrates, it consumes water, not just the process itself.
But not as much as
The plastic.
The other thing, how we are going to test the non-contact
Non-coil with pipes or without pipes?
with pipes, for example. Anyway,
How are we going to transport it?
yes, are you going to test it vertically or you are going to test in frame on the ground and test horizontally?
Right. All the pipes, all the specimens are tested.
The longest was 1.8 meter or 3
3
meters, so that will be tested vertically on the structure floor.
Yes. Dr. Ahmed is asking how he's going to transport the specimen. So Muhammad talked about preparing a handle.
The unconfined one.
The unconfined
The
is,
meters in height.
will be transported.
We're going to remove the plastic at the very end, with the cutter. And we're going to transport it with the pipe, and then at the very end, we're going to cut off the pipe.
But you said you had problems with really just taking the plastic out before.
No, at the beginning, before, what we did was we casted them in pipes that were cut vertically initially. But this time, they're going to be filled pipes. The pipes will be complete. And then in the place of testing, we're going to cut up the pipes. It leaves a scratch on the concrete, but it's no problem. It won't affect anything.
I have a small question, and actually it's a direct question. What could be an outcome? Of course, I don't want to predict data here or so, but what could be an outcome really substantial or tangible out of this work?
A factor that tells us how much confinement adds to the axial strength of the concrete core.
Okay. معلش كده وبعدين and then once you know this factor, what could you do with it?
Can compare this to a reinforced concrete column, the strength of it.
In other words, what is the application or the practical aspect of knowing this factor? I agree with you, it's a very useful piece of information.
For example, in hosted houses, you can use PVC tubes filled with concrete. They're not non-corrosive, they're lighter in weight, they're easier, they're more practical than steel, and circular columns especially. These smooth, even surface, and no need for plastering, no need for shuttering, and all.
I don't know whether I shared this with you and Muhammad Adawi before, but Canadians are very much going in that direction recently. There's like plenty of papers and publications in that direction.
You mentioned that the volume of the column will not change. Did you mean because it is confined or general? Because if it is general, actually you have something called bifurcation. You have a certain concentric force causing a normal stress, and it is functioning with Poisson's ratio and the Young's modulus and the modulus of compression also. Did you check that, or you mean because it is confined?
I'm talking in general.
Bifurcation is the change in volume divided by the division in volume. Did you check it?
I think Dr. Noor has a question. Raise his hand.
I'm seeing the diameter of the column to be 150 millimeter. And in practice, probably we need bigger pipes. Any idea about how far in diameter can you go with this technique?
In practice, there's some pipes that could be up to around 20 centimeters. But we could go up when we're looking in the market for pipes.
Not necessarily you can force the pipe, but
Can go up to
in terms of a bulk of concrete without steel reinforcement. Any idea from the literature how far in diameter can you go?
find relevant to
After checking the blanket, the damages you found, or
No, probably in the lab this is good enough, but I mean, in practice, we can find you a pipe that's big enough. But will your results still hold for the bigger diameter pipe or not? This needs to be investigated. I'm not saying this, you need to do this. I'm saying this is important in terms of looking at your results and making use of them in practice.
Okay, I have one last question. Going back to Dr. Muhammad's comment when he asked for the factors that you want to get. The factors, basically, what are you going to do with it? Now, in order to use these columns in the design, I have to know the capacity. Then the factors will probably help me to design these columns with some sort of safety, right? So that's why we are doing this work, that to demonstrate the additional strength that we can get due to confinement, so that we can use it afterwards in the design practice.
Sharif, I have two comments on what Sharaqa al-Mawla is intending, if you allow me. First, please watch for the safety measures when you do the work. I get concerned, as you know, so I want to say that. Second thing to Sharif, I very much like the fact that Kareem and the CA are taking pictures and videos of all of the presentations since last time. And I asked our friends here in the 490 groups to benefit from it, to watch how they perform, learn from it, and also to keep it as a souvenir to show their kids one day each one. So I think it's a very good practice that the 490s videotaping videotaping all these presentations.
Okay, thank you very much.
Thank you.